Okay, so I hope you can all see my screen now. My name is Sebastian Wolf, and I'm a PhD candidate at Technical University in Munich. And one of my main tasks is to develop SeisSol further. So I'm introducing new models, and I'm taking care that these models run fast. But today,
Sebastian,
yes?
could you minimize your picture, the Zoom picture, because we're still seeing them. Seeing your video.
Okay.
Yeah.
This
okay.
black thing.
Super.
Yes. Yeah, my main task is to develop SeisSol further, but today I will show you how to run your first dynamic rupture simulation. And first a short, small recap what dynamic rupture is. So we have a few ingredients here. So we have Coulomb friction. That means that the fault strength, which is the product of friction coefficient and the pressure, is always larger or equal to the traction on the fault. And either the fault is locked, then it's truly larger, or it's sliding, then there's the equal sign. We have a friction law, so our friction parameter mu depends on the slip rate S and on some state variable phi. And once we have a slip rate, we impose this as an initial internal boundary condition and couple it to the wave propagation part. So all in all, this is a rather complicated model, so it's not easy to verify these. And there is this benchmark suite, so there are a lot of TPV problems. This stands for the problem version, and then 5 to, I think there are like in total around 50 different ones. And today we will have a look at TPV13. And so this is a community effort, so everybody can upload their own solutions. You can see an example here on the right. This is a synthetic slip rate profile over time at a specific point on the source. And you see that all the solutions by the different people somehow coincide, so you can say this is the truth then. Then let's go to this TPV13 example, which we have. So we have a homogeneous elastoplastic material. This means that some of the deformation is permanent. And on the fault, we have a linear slip weakening friction law, so one of the simpler friction laws. We have a 60-degree dipping fault, and then depth-dependent pre-stress. And in particular, to initiate rupture here in this 3 by 3 kilometer patch, we have a lower friction than everywhere else on the fault, and this is then the nucleation for the rupture. So let's have a look how this works. First, I downloaded the benchmark description. So this is a quite long but very detailed document. It has the same picture, and then it has like all the description of the geometry, material parameters. Here's the pre-stress described, and then further down we have even more stress. Then we have the friction coefficient. So you can find everything in these documents, which you can download from the benchmark description site to set up your benchmarks, but to set up your simulation. And every one of you should see kind of that. So this is the Jupyter lab. I opened the parameters file already, but let's go to the main notebook. It's here. So again, there's a small introduction. And there are several ingredients to a SeisSol simulation. The first one is a computational mesh. As we have seen earlier, we use tetrahedrons, and we use Gmesh in this training. So Gmesh is a open source mesher, and here we define the geometry, we define the size, for example, then we create a box, we create a fault inside the box, which is a rectangle, and then we rotate the fault by some certain angle to get this dipping fault. We intersect everything with each other, and then we set a desired mesh size, and we set boundary conditions, and then this is the description. So this was really fast, but you can come back to this later and change this if you want to have your own simulation. It's a good starting point, so you can change parameters, and we will do this also later during the training. Then there's this gmesh command. I'm just going to run it, and then you will see that gmesh is running. It creates meshes, it creates TETs, and yeah, all in all, you see that we have about 42,000 elements. It's yeah, Elise, raise your hand.
Yes, just one question quickly before we are going to running this notebook. Is everyone seeing this in your browser? Is everyone with us?
Okay.
Are you all at the same? And if not, please give us some thumbs up if you're actually seeing this this notebook popping up in your browser. Thank you. See some thumbs.
Okay, great.
Okay, if not, please post on Slack now so we can help you, right? So you follow these steps, and this is a nice way to run the Jupyter notebooks in Docker using your browser. Okay.
All right, I'll just continue, and you interrupt me when there's something I have to explain in more detail. Okay, so this is the gmesh output. It's a command line program which we have embedded in this this Jupyter notebook. So we have now around 43,000 tetrahedrons. It's very small, but then it will run on your laptop also. And gmesh has its own format, but we need to convert the mesh to our own yeah, kind of optimized format. We need this tool is called PumGen. It generates parallel unstructured meshes. So this is a PUM and then generate. And I'm going to execute this command. This is really not interesting. It's just saying that what it's doing. And now maybe to the first interesting thing, we have a small visualization built in here. This is not as, I'd say, advanced as PowerView, but it will give you a first overview. And it's taking quite some time. So, but here we have our mesh. So it's a box. You see only the surface, so it's triangles, but I assure you there are tetrahedrons inside. And you can zoom in here, and we see the fault, and you see that the density of elements is larger here, and the mesh size is smaller. So we have a refinement across the fault, along the fault. And unfortunately, in this view, we can't have a look inside the mesh, but there is the fault actually in the mesh. Okay. And now we're going to run SeisSol for the first time. So this is the command. If you're following along, there's this OMP num threads parameter. You can change this to the number of cores which you have in your laptop. So for example, I have 8 cores in my laptop. I changed this to 8. If you have a even like fancy desktop machine with 16 cores, you put 16 there. Then there's MPI run minus n minus 1. This is relevant if you're on a cluster. You can put more larger number of nodes here. Then we have the SeisSol command. It looks like this, has some information built in. For example, the architecture. So this is optimized for the Haswell architecture. And then we have a link to the parameter file. I just execute this, and then you see a lot of information. It's like more or less, hello, I'm SeisSol. I'm running with a lot of parameters, and I'm giving you a summary. And then if you're scrolling down, you see there's a start. And then it says it's writing some fault output. It's writing some wave field output, free surface output. We will have a look at that later. This means that SeisSol is successfully running, and if everything is good, there should be a new output coming soon. So it's still running. So this might take some time. Yes.
Exactly. This may take some time. There's a question in the Slack of how long this would take, because Charles is running this already since, what does he say, 30 minutes on 4 cores. Oh, you already said 4 cores. I was asking if he has more than 1 core.
It shouldn't take too much. So it's like, what is this? A bit more than half a minute for 0.5 seconds of simulated time. And I'm having a quite recent Intel 5, nothing too fancy, but just a standard recent laptop. But
and the total simulation time is 15 seconds, right? Or 10 seconds?
No, 8 seconds.
8 seconds.
So it should take you about a little more than 5 minutes. Yeah. In the meantime, okay. So are you still having problems with running it, or maybe you have to shut down different stuff which is running at the side? Yeah, I just wanted to have a short look at the parameter file. This is yeah, more or less it just gives links to the material file, to the fault file where we define fault parameters, and then we specify the output. So here, for example, we have the output interval for the fault output. We have the name of the mesh, and then we have an output prefix here. And in the very end, we have the end time. And so this is set to 8 seconds. And if you're running really slow, you can reduce this to, for example, 2 seconds. You will see some part of the rupture already, but you won't get the full picture. And maybe we can have a short look at this YAML file. So we have the fault.yaml. This is more or less describes the friction parameters. So we have these static friction, dynamic friction, critical slip path or critical slip path length, and some cohesion. This can be all found in this document here. So this is exactly what we have here: static coefficient, frictional cohesion, and you find these values in here. And as I've said earlier, we have a patch where there's a lower friction coefficient, and we have kind of a box filter, and we say inside this box we have this friction set of friction parameters, and then everywhere else we have this set. Then if we go along, we have the initial stress. So this is again a bit complicated, more complicated, because we have a depth dependent pre-stress. Also, we can find the formulas here in the PDF. So it says, yeah, like some value times depth in meters is the stress, and then we have this here, and so then this is twofold. So above a certain level, we have more complicated stress, and then below a certain boundary, we have this more simple stress definition. And then the last file needed for our simulation are the material parameters. So we have the density rho, and then we have the 2 Lamé parameters mu and lambda. Unfortunately, here, if we go up to the PDF, if we go up to the material properties, we have shear wave velocity and then pressure wave velocity, but you can exchange all these different parameters. And then you can change them here if you want to have another material. But let's have a look at our simulation. So it's still running. It's slower than I expected, slower than yesterday. Maybe, I don't know.
Because of Zoom.
Probably because of Zoom. Zoom is taking away some of my computational resources at my laptop. So who has this running? Who got this running? So I'm going back to the Zoom window. Is there like, maybe you can speak up, because I can't monitor the chat that easily on the side. Okay. Yeah. Anyways, when you have this running and you're impatient as I am, you can go back to your terminal, and you can see here on the left, I have my server running. So I started the Docker container here. Don't wonder, it's called Podman at my system, but you can just explain, use Docker. And then I want to access the files inside the Docker container, and so I'm having a look at what containers are running. So here there's the name of my my container. It's running under the name Inspiring Morse, and I do Docker copy, and then I copy from the inspiring Morse container, and I take the I go copy the directory home training TPV13. This is the path inside the container, and now I'm can type a file name or directory name outside of the container on the host. So I'm calling this TPV13 container. Now it's copying, so I go into this directory, and then I see a lot of files in here. Maybe I'm doing it like this. So you have a lot of files. You have the mesh file here, and it's the XDMF and the PAML file. This is the mesh, and then you have the MSH file. This is the raw Gmesh output. And then we have this output directory. We can have a look at that. There are all the files in the output, and let's have a look at them. So I open my Power View, and I will go to where this is. So no, it's not there. Where is it? Okay, I have to search the files on my file system. So here's the output, and maybe let's have a look at the fault first. So let's select this fault XDMF file. So we have the prefix TPV13, and then SeisSol adds a minus fault and adds TPV the XDMF, and so we can move around, and maybe let's have a look at the friction parameter. You can select a lot of quantities here. MUD is the friction, and you see that we have this fault is largely at 0.7, and then we have this low friction parameter. And or we could have a look at the normal stress on the fault. So this is PN0. 0 stands for initial, including the initial stress. So we have this the stress profile on the fault. Or we can have a look at the traction in dip direction, or we can have a look at the traction in strike direction. And you see this the scale changes. So this is in the magnitude of 10 to the minus 7. So this is really small compared to the values of 10 to the minus 7, 10 to the plus 7 here. So what you see in here is more or less numerical error, and in here these are actually actual values. And now we can use these buttons on the top to go ahead in time. And so what happened after 1 second, we saw that apparently some rupture has happened, because our picture changed here, and we saw that the attraction dropped to some reference value, and then we can have a look at the friction parameter again. We also see that our low friction patch has grown, because where there is friction, where there is rupture, the friction parameter will decrease. And what else can we have a look at? There's ASL, which stands for accumulated slip. So we see that we have already some slip in this patch close to where rupture nucleated. And you see that, rupture is growing, or the rupture patch is growing, and we have almost no slip here in the outer parts, and no slip in most of the faults. So now we can cycle through. And you see that this color bar saturates after some time. So we can maybe do 2 more steps. Now we don't see a lot. There's a button to recompute the scale here. So now we have different color bar again, and our image is not overly saturated. And okay, let's go to I have computed up to 4 seconds by now, and this is the also more or less final slip. Let's have a look at the notebook. So okay, it's still computing. So at 7 seconds almost done. Now I'm going back to ParaView, and yeah, Alice.
Sorry for interrupting. I just wanted to highlight that there is a link that I posted on Slack with the complete simulation output that we prepared. So if your simulation is still running, or if you experience some problems on M1 and M2s, also ourselves when testing, so you can download that data set and open it up in ParaView and at least follow along with looking at the fault output, what Sebastian is doing now, looking at how the fault breaks and how much slip there is happening and so on, even if we have some trouble since we're going quite fast.
So. Yes. But I think I don't have too much time left, right?
It's okay, you can go a bit longer. I think it's the first example. I'll make sure that it's also very illustrative. Just want to highlight that this Rupture is going super shear close to the free surface. You can see this with this, you see this kind of faster Rupture front there. That's very interesting.
That doesn't really work. This because of resolution. We have a Rupture velocity output. It's called VR here, but with these low resolution models, you see that there's some numerical inaccuracy happening close to the free surface. So that's why it's not too illustrative. Let's go back to this accumulated slip picture, and let's have a look at the other output. So we have a surface output also. This is kind of relevant. Okay, I was having a oddly oriented view on the fault all the time. So we have the free surface here. So this is the top. And of course, this is rather relevant if you thinking about earthquakes, because you want to compute some shake maps or whatever. And there are different quantities. So U is the displacement in either X, Y, or Z direction. And then these V's are the velocities. So let's have a look at the vertical displacement. And you see that here we have some uplift on the further side, and we have some down fall here in the front. And unfortunately, you maybe want to have a nice looking picture for a publication, as you've seen before. So the free surface is kind of blocking the fault, so you can't see both at the same time. But yeah, ParaView has some nice features. So you have a clip here, so you can restrict the free surface to only part of it. There's this arrow. You can move this around. Let's say we want to have it like here. Let's hide this plane, and then we want to say here we want to have the vertical displacement. So now you see that there's uplift at the this side here, and then we have downfall at this side, and then you can combine all these different outputs we have to get a nice visualization for your publication, or to show your colleagues and discuss what's happening there. Let's have a short look at the volume output. The volume output is very memory consuming. In this case, it's only about 50 megabytes in total, because we have a rather small setup, but this can really be an issue when you have large-scale production runs. So now we have this whole box here, and we can now have a look at U, V, and W. These are it's a bit misleading. So these are the velocities now, not displacements. Or we can have a look at eta. Eta is this this damage parameter, which comes from plastic yielding. So we see that we have some plastic yielding here. Maybe I have to adjust the color bar such that we see it better. Let's have it from minus e to the minus 5 to e to the minus 5. So okay, this was a bit too much. So let's remove one of the zeros here. Okay, now we see that we have plastic yielding almost here around fault, and then we want to see what's inside, and So we can't really look inside earlier, but with ParaView we can, because we have this clip and we feature. So I'm just cutting this box in half, and now I can add this iter parameter again. So now we see where plastic yielding occurs. So it occurs, yeah, mostly close to the free surface and in some kind of, yeah, it starts here at the fault, but also carries on along the free surface. And so we can have, we can combine all these three plots now. So I'm activating the free surface clip again. Okay, so it's a bit, okay. Yeah, these are the subtleties with ParaView. So you would need some more time to make this work really, to make this work nicely. But you have an idea what you can do. You can activate different things, and this is good for creating plots for papers and publications. But it's also really interactive, and you can go around and yeah, explore the simulation results by yourself. Okay, so let's head back to the SeisSol output. So here we see we're writing output at time 8, which is also our final time. And then also then there's some summary about yeah, computational flop counter and stuff like that. And then SeisSol says goodbye. Yeah, if you're having problems with ParaView, there's also a visualization toolkit like in this container. It only visualizes the fault. So looks something like this now. If you, yeah, I would really recommend using ParaView. If you can't use ParaView due to, I don't know, whatever problems you ran into, this is a good substitute, I would say. And okay, then we have a small exercise to actually change the dip angle here and see what changes. This would maybe take some more time because yeah, computations are quite slow. So maybe we can, are there any questions so far which I should answer, or should I just go along with the changing the dip angle?
I don't see any questions in Slack besides one trouble.
Yeah.
I think it would be nice to change the dip. You know, there's lots of things we can see. Super shear rupture nucleation will change. Off-fault damage will change. So maybe we do this one. Okay. Yeah.
Yes. So first, we have to go back to the mesh creation, because as I've said, the fault is part of the mesh. And when we have a look at this geo file, we see some parameters here, and there is already a dip parameter. So when I run this gmesh command, I can just add a set number command. Then I have to define which kind of number I want to set. So I want to set a dip, and I want to set it to 45 degrees. Now gmesh is running. Okay, gmesh runs successfully. Now I have to convert it to the SeisSol format again. And okay, I could visualize it, but you won't see anything because the fault is hidden. Now we could just run it again and see what happens. I'm going to jump a bit ahead, because first I have to change the parameter file. So I want to save this somewhere else to make a comparison later. So I'm adding a dip 45 here to the output prefix. And since I have some hard time computing, I'm just going to change the final time to 4 seconds. So we won't get the full picture, but we will see something. And I have to change some other stuff as well. So if I'm going to the to the fault here, we see that we have this this low friction patch in a specific position. So we haven't changed that, and if we change the dip, then we have to move up this friction patch. And I pre-computed some values, so we have to move it up. It's now between around 9,500 and let's say what's it, 7,500. And also, since the stress is differently at that depth, we have to remove we have to lower the friction parameters, because otherwise we won't get a rupture, because the fault is not over pressured then. So let's change these parameters. These parameters are done such that we actually have a rupture, and let's make sure I've put the dip 45 there. Yes, I did. And now let's run SeisSol again, so we can go back to our Jupyter notebook and just run this. So SeisSol is saying hello again, and initializing a lot of stuff here. And you've seen that it started computing already. Now there's a problem I have with my Docker, so I always have to remove the this directory, but then I can just use this copy command again, and then I can go back. Now I have everything copied from the container into the host again. Let's go to the ParaView, and I just keep all this stuff here in my pipeline, and I'm going to open a new file, and we already see that we have the dip 45 version here, and I'm going to open the fault, and then you see now this is the nice thing, we can have both faults in the same picture. So you see they have the same location at the surface, but now they have a different dip, and one has broken already because we had 4 seconds. This is some ParaView feature. If I say plot me this solution at 4 seconds, and my dip 45 simulation hasn't run that far, it just gives me the initial value. But we can analyze that. So let's have a look at the friction parameter. We have lower friction now here, and we have this nice patch again. We can have a look at the maybe the traction in dip direction. So this is like this, and you already see that we have some rupture starting here. Let's see how far we have gone. Okay, like 1 second. Okay, so I have to remove that again, copy it again. Now I should have the results after 1 second available. Let's go into ParaView. Let's select my dip 45, and I have to press F5 to reload. Then I can say reload existing files, and then it reloads the thing. And now we see that the rupture has initiated. And let's go to 1 second, such that at 1 second, I want to somehow compare them, but I don't see the 60-degree dipping fault, so I'm adding a clip to the 45-degree fault. So I'm seeing both faults at the same time. Maybe this is kind of good. And I want to compare the friction coefficients on both faults. So let's select the 60-degree fault. Let's go to the friction coefficient. And we see two things here in the middle, in the parts where friction or where rupture already has occurred. We have gone down to 0.1, and if we go back to the benchmark description, friction coefficient of 0.1 is just the dynamic friction coefficient. And then in the 60-degree dipping fault, we have a parameter of 0.7, which is outside of the rupture area, which is what we have prescribed there. And then we see that in the 45-degree fault, we have a friction parameter of 0.5, which is this is just what I have changed it to in the parameter file here, to say that we still have some runaway rupture. And maybe we also want to have a look at the peak slip rate. PSR stands for peak slip rate. Let's compare peak slip rate. So we see that after 1 second on the 60-degree dipping fault, we have a slightly larger slip rate than we have here. So this is also like an interesting result that we have. And maybe how far has my simulation gone here? Okay, until only until 3 seconds. Let's have a look at the 3-second output. I'm going to have to remove the container copy and copy it again into the host. So now I have to press F5 again. Now this there wasn't this question if I want to reload files or want to use the same files. It's just another paraview subtlety, and now we can click through it. So let's go to 3 seconds, see what has happened after 3 seconds. We can again analyze the peak slip rate here. We see that it's consistently larger on the 60-degree dipping fault. Maybe as a last result, let's have a look at the slip rate. Okay, have to choose this one. So slip rate, SRD, this is the slip rate in dip direction. This is the current slip rate at 2 seconds, and the peak slip rate is the maximum over time. So let's have a look at, let's compare the current slip rate. And you see that, yeah, the picture is kind of symmetric, but we look at this, you see that on the 60-degree dipping fault, which is the lower one here, rupture has not propagated as far outwards as it has on the 45-degree dipping fault. So that's a lot of stuff you can see here, and you can really analyze what is happening on the fault during the earthquake, and this can give you nice insights into earthquake rupture. And yeah, with that, I want to start. This is everything I want to show you for now. You can have a lot of fun with SeisSol, with these simulations. After a lot of years working with it, I still think it's nice to have a look at these pictures and imagine what's going on there. And if you have any questions about what I just told you, please go ahead. I hope you could somehow follow along and redo what I did.
Very nice, Sebastian. Should we also share one example output with another fault dip geometry? People can play with that in ParaView.
Yes, I can upload my 45-degree solutions
sure.
in a second, and then people can compare the 60-degree and the 40-degree versions by themselves.
The issues that were popping up on Slack were mostly not related to the physics, but related to either Docker ports or Docker architecture or M1, M2. But you can have a look. Maybe there's anything. Nobody gets excited about the super here, but you will in the last example, I tell you. Okay.